All right, you've waited all semester for this. We're ready to start modeling physical systems. We're going to start with translational systems. Okay, and so here's the standard one, a mass spring damper. All right, so let's start looking at these parts. What do we have here? There's a force that's applied in the damper, and as this mass moves, the spring will oppose it, and the damper will oppose it. So we need to talk about these various elements. So mass is modeled by the sum of forces equals derivative of the momentum. Now for our problems, we'll generally have the mass as constant, so that leaves us with ma for constant mass. And the thing to note is ma is a resultant of motion. It is not a force. Okay, this is important. So we have to keep that straight. And I'm making a big deal about this. And by the way, so the sum of all forces equals ma. Mass represents resistance to acceleration. The bigger this is, the less the system will accelerate. But this is not a force. And I'm making this point because there was a professor at a world-class famous university in the States I'm aware of, who made up a final exam where he had basically set up MA to be a force, which is pathetic. You should not be a professor if you have that um, misunderstanding. Anyway, friction and damping. It's a good thing in moderation, is what I would tend to say. Because if you were constantly walking around on ice where there's no friction, you couldn't get anywhere. So friction helps us. Just don't need too much of it. All right. What direction must forces due to friction have? The opposite of your motion. They go in the opposite way. What is the friction force on an item which is motionless with no external forces? So this eraser that I just put there. What is the friction acting on that right now? Zero. Friction is a lazy force. If you don't need any of it, it doesn't give any. All right. So if you're not moving, if there's no friction, it says that relative to kinetic friction, it is ultimately some function of velocity. You got to be moving to have it. All right. So we have various kinds of friction that we can model. Viscous friction occurs when a mass is sliding on an oil film, all right, with laminar flow in the film. So it's something like what we see here. So we have some horizontal surface. There's some oil film between here and the mass. This surface could be moving. The mass can be moving. And then so the friction will oppose the motion. And so here's what you would have. F equals minus B times V1 minus V2. This is just our damping caused by the scenario. So we model that what that B is. Okay, but it's a constant. All right. Now, this is with laminar flow here. Let's consider a simple shock absorber. Okay, so we have a piston that has holes in the piston top, and as this tries to move in, the water, well, the fluid, hydraulic fluid, whatever's in here, will resist it, but it can move through the holes. And so as it moves through the holes, and the shock absorber will move in. This can result in very high flow rates that aren't laminar. And when this happens, we can get a function, say something like this, minus b times the absolute value of v times v. So it's basically a velocity squared in here, all right? And from my understanding of aerodynamics, as speeds get even higher, this is called drag, by the way, when you're a function of square root of velocity. But you can have regimes where this becomes not v squared, but v cubed, okay? And as you go in, if you go into some aerodynamics and things like that, you'll learn about that. All right, so different kinds of friction. We will tend to model everything with viscous friction, but we should note that you've seen another variety of friction in your that's commonly used in statics and dynamics courses, and that would be dry friction, say a box sliding on a floor. All right, and here you have the coefficient of static friction times the normal force is the value that it is pushing against you. This would be the difference between the speed of the floor, typically 0 in the box. So it would oppose you, and of course you have the coefficient of static friction, which isn't a big deal to us right here, simply because this whole course is about things that are moving. So you've gotten past the static friction. We're not going to have to worry about that at all. And as I said, we are going to tend to model things by viscous friction. So it'll be, you may go, well, why didn't we use this one? Well, because we're looking at machines. And here's the thing. When you're looking at machines, most stuff is lubricated. All right, you're not usually going around sliding boxes on floors. So we're dealing with purposely designed systems. And so they're not going to tend to have dry friction so much because they'll have some sense of lubrication. So the viscous friction will work for us. Now, we should note that the model for viscous friction tends to fall apart at really, really low velocities as almost a dry friction comes into play. And so instead of being just a proportionate to velocity and going down to 0, you still have some level of friction. So I'm just letting these things kind of, rather than going down to 0, letting them come off like so. But that's not a real problem, okay? Since the real friction is actually higher than the model would project, it means that this friction will cause the thing as it slows down to stop more quickly, all right? And so that makes the model more conservative, all right? So when you're projecting something will settle in 1 second because of this kind of effect, maybe it settles out in 0.9 seconds. So it's a more conservative situation. We're not modeling this, but we don't need to. If we get acceptable performance based on our specifications, we can expect that it'll settle out a little bit faster. So that's not a big problem for us. All right, so that's what we're discussing there. So we've dealt with damping. Next step is stiffness. So any mechanical part that undergoes a change in shape when subjected to a force is modeled by a stiffness element, and we're usually talking about springs. All right, what is the force of the spring? It'll be a function of distance or displacement, x. You can have springs that are a function of the square of x, the cube of x, the square root of x, oftentimes just linear with respect to x. We're going to be dealing with linear springs, and so this is, you've seen them in your dynamics course. A linear spring is simply the spring force equals minus kx. As the mass moves by a distance x, the spring opposes the motion. Okay, so we get something like so. All right, now we will quickly note that there are many kinds of springs that are used in mechanical systems, so I'll just take a moment to note those. Leaf springs, you see them in cars and trucks all over the place. Coil springs, a slinky, they've been around. You'll find them on your garage. Cantilever springs, can't think of a time where you see that, but this is more of something you have to model in building structures, so you can have that. Torsional springs, this will be for machines as they rotate. You can have torsional springs in there. So those are a number of kinds. Again, we're going to model everything as a linear spring. So I will, this is our introduction. I will leave it at this point, and I'll see you again soon.